before I continue to more uses of infinity, I just realized I wanted to say whether like a calculation like flat out 1 over 0 equals infinity would show up when you're using extended reals in measure theory. I think you could, but it's really not the kind of thing that infinity gets used for. Infinity is usually either the size of a set or a limit value of a sequence of functions, and not generated by just dividing one finite number by another. So I wouldn't say that's a great place to say, oh, hey, we finally found a place where you could just really say 1 over 0 equals infinity. But so let me turn to a really general thing. It goes under the heading of compactification. I'm not going to talk a lot about the topology behind that phrase, but that word. But let me show you one of the simplest examples, and that would be called the real line union a point at infinity. And notice this is not a plus or minus. There's just going to be one point at infinity. So there's a great picture that goes along with this. So take the real line, think about it sort of geometrically. I want to think about a way to have finite numbers and then include an actual point that serves as the point at infinity. And it's going to be a point that you get to if you go arbitrarily far, if you go far, 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 far along this way, and you'll get to the same point if you go far along this way, and so you can actually kind of wrap around. Well, that sounds like a circle, and there's a nice way to actually map this to a circle. So take a circle and put it right on top of the line, and then take a base point right at the top of the circle. I'm going to call it the North Pole because we'll do this with a sphere eventually. And then do what's called stereographic projection. And that means we're going to define a map from the circle to the line by just mapping from the base point to boom. So like maybe it hits at 3. So this is going to be my new place to put the label 3 here. And then boom, 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 boom. I'm going to put a 2 here. I'm going to put a 1 here. 0 is going to be right down at the bottom. Here's where minus 1 is going to be. And you can convince yourself, hopefully, that you're going to get every finite place because like no matter how far you go on the circle, on the line rather, that's going to connect up to the North Pole and it's going to intersect here. Now, places that are really far out here on the line are going to show up really, really close to the North Pole. And similarly, over here on the other side, those really big negative numbers are going to show up really close to the south, to the North Pole. So that's interesting. We've already done something significant. Even if we don't actually add an infinity, we've tamed huge numbers to some extent by just saying that when you get to really, really huge numbers, and if you watch some of the other videos I make, you know what I'm talking about, you can just actually think of them as just being ones that really, in their images on the circle, crowd up really close to the North Pole. And then it's really tempting to say, hey, let's put a label. There's going to be one point missing. The North Pole isn't going to be the intersection of any of these lines from the North Pole down to the baseline. It's not going to be the intersection of any of those honest lines, but let's just say, hey, let's add that point to the space to be infinity. When you're on the circle, that's incredibly natural because the circle already has that point. And so when you're on the circle, it's something that's like, well, why do I want to leave that out? But the cool thing is that then represents infinity. Okay, so you can either think of it as taking the real line and just adding a formal point at infinity with various properties, like if I go out as far as or keep going out in any direction, I'm getting closer to infinity. Or you can think of it with this model as the circle, and it just happens to be the North Pole on the circle. Nothing really weird about that. It's very, very cool use of topology of appropriating a new space that's familiar in one setting and has no weird properties, there's a lot of good properties, and thinking of it in a new way to say, whoa, this is now a model of what happens if I take the real line and I add a point at infinity. So it's what's called a compactification. R is what's called a non-compact topological space. You can kind of run off to infinity. You can run off in some direction and forever and ever and ever and not get anywhere. And the circle is what's called compact. That's not true of the circle. You can't run off to infinity. So this is a classic case of the compactification of something. So how do you use this? Well, for example, let's say we had the graph of like y equals f of x equals, instead of just sort of points, we got to figure out how this works in functions because this is all about analysis usually, or at least algebra or algebraic geometry or something. We got to do something with these fanciful ideas. So let's just take this function. If you graph that function, it's not hard to see. It goes up like this and then comes down Goes down like this, comes up like that. Not a ridiculously complicated function, but I wanted something that just wasn't like 1 over x. And I'd like to say that when I plug in infinity, now I've got an honest to God point at infinity that I could think about, does it mean anything to plug it into that function? Okay, so to be careful for just a few seconds, I'm not trying to be super careful in general in these talks, these videos, but what I really mean is there a natural extension of the function defined by this formula? Literally, this thing only really works for a real number over a real number. But is there some natural extension of that formula? Let's say I insist that it be continuous, that would actually have a value at infinity. And indeed, there's only one way to extend this continuously to the point at infinity, because what we see is that as the numbers we put in for x go to 1, 10, 100, 1,000, a million, a billion, the output values get really, really small. Okay, and so if there's any meaningful value here for f of infinity, it's going to be 0. Okay, so we're getting really close to saying I'm sort of dividing by infinity, because it's almost as if you're taking infinity over 1 plus infinity squared. Now that's not really what you do. And really anytime in the rest of these videos, if I ever write 1 over infinity, to really unpack it carefully, you have to really do something careful. And you're not literally doing algebra with infinity, but it's going to come really close to seeming that way. So this means that the unique, I'm trying to make my cue better, the unique continuous extension of f, we could maybe even decorate it with a little tilde or something, to this new cool space, the compactified reals, and we'll call it f tilde, has f tilde of that point give 0 as the output. Okay. We could also do it on the circle. We could say, look, f is really now thought of as a function on the circle, giving real values on the circle, and f at the North Pole, which is totally fine. It seems like we extend it to have a value at the North Pole, and its value at the North Pole should be 0. That would be a nice way to say it. Okay. So how do you tell, in more generality, how do you tell, if you don't graph it or analyze it carefully, whether this is going to be nice at infinity? Not every function behaves nicely at infinity in this sense. And a nice way to do it is we just want to have a tool, essentially a coordinate system. There's a nice way to think about it where we introduce a coordinate system, kind of like polar coordinates, things like that, that works well near infinity. What does near infinity mean? It should mean for big numbers. And the bigger you get, the nicer it gets, or the more predictable it gets. Okay. Well, in particular, this coordinate system should take the point infinity itself and take it to something super simple. Hey, what about 0? Okay. So here's what you do. In this case, you have this function. Let's go back to this function. I want to answer more than just, okay, does it deserve to have a value at infinity? I want to ask questions about, like, is it differentiable at infinity? What the heck would that mean? Okay, well, a nice way to do that is if we can use a coordinate system that translates a question about near infinity to a question about what's happening to some related function near infinity, near 0, then that's more okay to talk about. Okay, so here's what you do. You just plug in 1 over x everywhere, because 1 over x is certainly a function that takes big numbers to small numbers, and the bigger the denominator gets, the smaller the numerator gets. Okay, and so I plug that in. I multiply by x squared over x squared on top and bottom, and the cool thing, one reason I picked this example, is you actually get the same exact function. That's unusual. That's not what you usually get. Okay, but what this says, so now we analyze this near 0. Now again, to be a little careful, there's a little bit of a dodge, I said, by saying this is equal to this. And if you have a really persnickety calculus teacher who's focusing on this issue, they would say, okay, not really. These aren't exactly the same function. This function, this algebraic formula, evaluates when x equals 0 just fine to be 0, okay? So 0 goes to 0, okay? This function, because the first thing you're asked to do is take the reciprocal of x, this function literally, this algebraic expression literally doesn't have a value at 0. And what do we have a terminology for that. It's that if I look at this near 0, any non-zero value of x is totally fine, and you can do the algebra, multiply by x squared over x squared to get this, and so you get a function that looks like this with a big old removable singularity at the origin. Okay, this is a very common thing, use of removable singularities. I've gotten a formula for something where it's really trying to be nice at 0. There's no moral reason why this is doing anything weird at 0. It's just that the formula I'm using does something silly. It takes the reciprocal of x, take the reciprocal of x squared here. But you know what? It's essentially doing this. The careful language for that is that this literally doesn't give a value at 0. It's true. Just like I couldn't literally plug infinity into this function. I had to be kind of clever and say, oh, I'm going to fill in a value and justify that it's reasonable. Same deal here, but something you actually do in a first year calculus class. I'm going to say, hey, that's a removable singularity, a removable discontinuity, and I'm just going to create a slightly souped up function that just fills that in. Now, wouldn't it be nice if that slightly souped up function has a nice formula, a nice algebraic description instead of like some sort of piecewise thing? Oh, guess what? There it is. That's the function. So that's a more technical way to say it, is that when I looked at this f of 1 over x, sort of using 1 over x as a coordinate system to tame infinity, I get a function that isn't quite ready to evaluate at 0, but the process of making it nice is just the process of filling in a dot, removing a removable discontinuity, and the new version of the function in this coordinate system is nice. And it also happens, it's kind of cool to be exactly the same as the old one. So the cool thing about this function, you can say, this specific function, is that not only does this deserve to have a value at infinity, not only is it nice and smooth, differentiable, all these great things at infinity, its behavior at infinity, whatever question you ask, will be an exact mirror of the behavior of this function at 0. That's pretty trippy, and that's because I picked it to have this really nice algebraic property. Okay, so so this idea of using the 1 over x function as a coordinate system, and then, if necessary, removing any removable singularities, discontinuities, is a really cool one. Let me see. I'm getting some sunlight in here. I don't want. Okay. So where you see this more often is actually in the complex numbers. We start with the complex plane. I'm going to draw it, a finite plane. Want to think of it as going off to infinity. And we take the complex plane and we add a single point at infinity to it that you get to by going in any direction. The idea is you actually end up at the same point at infinity. And that's actually it's the right thing to do 99% of the time when you're when you're compactifying the complex plane. So it's called the extended complex plane sometimes. The complex plane with a point at infinity added, but it's often called the Riemann sphere. Okay, what the heck? This doesn't look like a sphere, but it's the same trick where you say, I've got a nice model of a totally well understood space that doesn't involve any explicit adding stuff at infinity. It's called the sphere. And we do the same stereographic projection. We use a base point, the North Pole, and we say the identification of a point on the complex plane, like let's say like 1 plus 5i, if this is like the imaginary and this is the real axis, the identification is wherever this dotted line hits that sphere, where that dotted line has been drawn from the North Pole. Same deal, every point on the sphere except the North Pole is exactly identified in a wonderfully nice continuous way with points on the plane. As I look at points on the complex plane getting really, really big, all that happens to the point on the sphere is it walks up the sphere and gets closer and closer to the North Pole. And then I just declare, hey, I've got exactly one missing dot. Notice it's very much like that removable discontinuity thing. I've just got a missing dot in something that just totally seems like it deserves to fill in the dot. I fill in the dot and I say, that's my representative for the point at infinity in the complex plane. Okay, and so the same idea about like using coordinate systems is nice as well. The official thing is we check If we want to understand any property of a function f on the complex plane, and we want to say, suppose, I want to know if f of z is nice, meaning does it have a value? Does it is it continuous? Is it differentiable? Is it complex analytic, holomorphic, various things that apply to complex analysis? If you check that if this is nice at infinity, by definition, that's going to be if f of 1 over z is nice. And I'm not going to say at 0 because I shouldn't literally plug in 0 here, but I'm going to say everywhere near 0. So does it have a removable discontinuity? If this guy has, when z is getting really close to 0, if this new function is well behaved and the only thing is I just was missing one dot like in my other example, then I would say, okay, f of infinity is defined. And if this function is smooth, continuous, whatever, I call f smooth or continuous at infinity. Okay. You can even do, so this is really cool because here the infinity can be an input or an output of the function. So you can do functions, and it's super useful to do functions that go from the Riemann sphere or extended complex plane to the Riemann sphere. I'll stop this one in a second here. It's getting a little long. So for a great example is just a little bit souped up version of like 1 over z. Say we have z minus 1 over z plus 1. So what's called a fractional linear transformation. There's a huge amount of theory associated with these guys. Geometry, group theory, number theory. It's incredible. And let's just do some values here. If I input 0, it's clear that I get minus 1 over 1 is minus 1. If I input 1, for example, oh, that happens to die. 0 over 2. Okay, I got 0. But if I input minus 1, I get something that's it looks like minus 2 over 0. Okay. Well, if you want to be really, really careful, we would take 1 over this quantity. 1 over. So if I want to check the output and see if the output seems to be giving me infinity, I just say, okay, is this quantity 1 over the output? Is that nice? Well, that's z plus 1 over z minus 1. Oh, when I put minus 1 in here, that's 0. Okay. So, and I just say, when the output approaches 0, the reciprocal of the output approaches 0, I just declare that that's something where the original output is declared to be infinity. So we really just say, yes, when you f of minus 1 equals infinity, when we're allowing ourselves to work on this extended complex plane. And then you can also put in infinity as an input, and you can always determine that just by taking a limit. The limit as z goes to infinity, well, if z is a honking big number, the minus 1, the plus 1 don't count, and so it's like z over z, and it's 1. So you could either say the limit as z goes to infinity, and it's important, no matter what direction in the complex plane, along the imaginary axis, real axis, diagonal axis, whatever, you can prove carefully that that's equal to 1. And that's a more careful way to say it. That totally makes sense in like a calculus class. But it's cool to say, actually, you know what? We're going to say f of infinity equals 1. Okay. So in particular, if you're really careful about what this all means and how it unpacks and what not to do, you can really say, let's say if f of z is the reciprocal function itself, then we could say f of 0 is infinity and f of infinity equals 1. So literally, I hate to go on one more minute, but I really should. I'm not saying that 1 over 0 is infinity, because that really sounds like I'm doing algebra with zeros and infinities in a way that we all know that's not possible. And I'm also not literally saying 1 over infinity is equal to, that's supposed to be 0. Just kidding. Hopefully you notice that. I'm not literally saying 1 over infinity is 0. Okay? But I'm saying that if you use this algebra to define this function everywhere on C minus the origin, so not yet at infinity and also not yet at 0, everywhere there it totally makes sense. And think about R if you want, if C is confusing to you, okay? Then the unique natural continuous extension of this algebraic function to the extended complex plane absolutely satisfies this. So if you wanted to be super careful, you'd be like, hey, this is the algebra version, and maybe put a tilde to distinguish, hey, I've souped it up a little bit to live on this bigger space, but in a completely natural way is the only reasonable way to do it, and I get infinity and 0 here. It's really close to saying 1 over 0 is infinity and 1 over infinity is 0. But I don't know if I want to actually literally write it down for fear that first-year calculus students are going to watch this and get totally wrong answers. Okay, I will wrap this up with another idea of compactification in a much shorter next video.